We just show the carry in the C column.
The C is completely separated in its own column.
So
it is not a part of the sum or the difference.
Right, that it should have been the full answer for binary sum with the carry and everything.
Right, so when you look at the binary sum and the binary difference, it should be exactly 4-bit wide. And then the carry and the borrow has their own columns.
Okay, that's what I want to make sure.
Right. Mm-hmm. Since I got time, I might as well download my new processor design because we'll be using that today. There's no homework yet for that one, but some of you probably can work ahead of the class and actually get something done. So it's still under binary numbers. It is the last one here, 2016 processor version 1. Save the file. Put it into downloads. W. Okay. All right. Minutes. You guys can hear the hum of the circulation, right? The air circulation. Yeah. They promised that the new building is not going to have this kind of issue. Yeah, they're going to take down all these buildings within a year. So the entire BCS division, or the majority of the BCS division, will move to the temporary buildings.
Oh.
Yeah.
That's cool.
And then they'll build a new building on top of these older buildings. And it's going to be a 3-story building. So instead of spreading out all the classrooms, it's going to be stacking up.
That's good, yeah.
And then physics and philosophy, physics and astronomy is going to move in with us. So engineering, physics, and astronomy, those 9 or 10 faculties will basically be joining us in that new building.
Yep. What happens to their current physics stuff?
Well, it's going to be vacated, so somebody else is going to move into that portion. I'm suspecting our new media and some of the other vocational edtech, not edtech, vocational education departments will move into their offices.
Dude, the first thing on the list, do take your personal time off.
Yeah, I haven't forgotten your email. I just haven't gotten to it yet. So I just want to let you know. The email, adjusting your score for the exam questions.
Oh, that one. Oh, okay.
Because I'm still in the process of grading, so
I understand.
I'll get to it. If I don't get to it, you can kind of give me another book.
I was so confused at first. I had another professor who I asked to do the same thing. We're using Canvas, and Canvas is having grading issues. So,
and we are all going to switch to Canvas.
I know, right? That's why we're the test dummies for this semester.
So who's so gung-ho to switch to Canvas this semester?
Professor, I don't remember his name, Lestrange was forced to do it. He didn't
Forced
have a
to do
choice.
it? No, he's not forced.
No, he was forced.
He was
As
forced?
in, he didn't come up with a book, and they were like, well, instead of using a book, we're just going to make you use Canvas. I don't know what the whole situation
What
is.
class is that?
CISP310 or C310?
C310?
They're pretty much forcing him to use this.
Huh.
Right, when,
CISC310, what do they teach you?
it's an intro to computer systems class.
Oh, I know that one. I refuse to teach that class.
I understand why.
I declined to teach that class because I completely disagree with the book they choose to use, and I really have a problem with that book being mandatory. It's an expensive book,
Well, he didn't make us buy the book.
but because of that, he had to switch to Canvas because the book is available as an online resource through
Except you can't even
Canvas.
get to the book online. You can only get to the questions.
Are you sure it's not D2L? Is it actually
It's
Canvas?
actual canvas.instructure.com.
Oh, wow.
Yeah, it's horrible. You'll read all of the text-based answers that you enter. Even if it's correct, sometimes it's spit it back out as wrong.
Well,
It
okay.
doesn't do a case
It
check.
takes a lot of tweaking, on the instructor's part to parse the answer correctly. Yeah, I understand because Moodle can have that issue if I do not, specify the key correctly. So that's a universal issue in a way. All right. Well, it is 9:01. I'm going to get started here. Okay, let me check. The recorder is on. Very good. Okay, so the do's and don'ts of political involvement. Okay, I got this email this morning, and I would like to share it with the class because I know most other professors is not going to share this with you, so that you know what professors are, and staff in general, what they're supposed to do and what they're not supposed to do. So I'm not going to go through the do's so much as to the don'ts, okay? Don't use district, college, telephones, email, computers, or servers to assist a campaign or to personally campaign for or against a candidate for ballot measures, okay? I usually don't do this unless the ballot is, let's switch from decimal numbers to binary numbers. Then I'm all for it, man. I'm going to use every single resource that the college pays for to promote that. But until such day, that's not going to happen. Okay, don't use college district paper, copier, fax machines. What are those things? Scanners, printers, and other business machines to print, create, edit, duplicate, or distribute campaign literature for or against a candidate or ballot measure. Clearly coming from someone who has not moved on from paper-based stuff to e-stuff, right? Don't use district, college, inter-office mail to distribute political materials. Don't distribute at public expense campaign literature prepared by private proponents or opponents of a ballot measure. Don't encourage or direct district college employees to spend their working time preparing material to support or oppose a candidate or ballot measure. Don't use public funds to purchase items like bumper stickers, posters, advertising floats, or television or radio spots. Now that is a little tricky because a good portion of my salary is quote unquote public funds. So that means I cannot spend my own money for any of these purposes, right? Unless I make a living or make money from some other sources that I cannot disclose. Don't campaign in favor or against a candidate or ballot initiative while wearing LRCCD, the district, ARC, CRC, FLC, SCC, or LRPD, that's a police department, badges, clothing, or uniforms. Have I ever?
I don't think so.
Exactly. Don't solicit funds from district vendors, like from our publishers, to support or oppose candidates or measures as a part of your contract discussions. So if you cut me a good deal on this textbook, and support this particular candidate, I might choose your textbook as opposed to the alternative textbooks. That's the kind of thing they're talking about. Don't solicit funds on college district property to support or oppose candidates or ballot measures during work time. So I guess, giving you guys a little basket to pass along in the class is out of the question now. Well, it only says something about funds, okay? So if you can give me items that I can sell, I guess that would still be okay. So just drop your cell phone in the basket. Don't provide only one side of the facts when responding to a citizen's request for information or any meeting when such information is requested by a public or private organization in your official capacity. Well, I don't even know what my official capacity is. So, alrighty. Well, okay. So now you know this, right? Because I think they put this up or send this email to everybody because some professors, not some profs, okay, but some actual professors actually talk about political stuff. They push certain agendas and stuff like that. So, and once again, unless it's about binary numbers, I don't really care. If it is about binary numbers, I will make it class business to talk about it.
So like the next president says, let's teach binary in grade school.
Yes, binary in grade school, but that's to help me prepare my students because I don't have to talk about binary numbers in my class anymore. I can spend more time to talk about the gate logic, how to write a program in assembly language and stuff like that. So it is curriculum business then, right? Okay, so let's get back to the homework assignment, flag assignments, and we'll go ahead and I'll go ahead and do it myself.
Then people didn't turn in.
Yeah, there are always a few.
I feel sorry for those people.
Okay. All right, so the recorder is on, and we'll just go ahead and take a look at, what is it again? Flags. All right. So as promised, I'm going to disclose the solution in a way that some of you will go like, oh, really? It's just that? Okay, because there are different ways of doing things, right? Okay, so as far as, so the first thing is we want to copy the numbers. That is only a problem, like if you see all the numbers changing as you type, it's only a problem if you use Excel. If you use LibreOffice, it doesn't do that, okay? If you use LibreOffice, does it change every time you open the document?
You have to re-initialize the copies.
Oh, so it stays the same.
That is good.
Okay, so that's actually a good thing. So that's basically what you need to do if you're using Excel is to just to copy the numbers. But if you're not using Excel and you're using LibreOffice, this will do. Okay, so I want to test this theory as well, okay? So we'll just go ahead and remember a few numbers. 210 is the last one.
The two rows on top, you entered yourself, so they're not going to change.
The two rows?
13 and 1, 11 and 6.
Yeah, those are just hand written. Those are hand copied. So I intentionally do it this way just so that I can test my theory. So we close this, and then we open it, and the other ones got changed, right?
That's correct.
They all got changed. Okay. But even that is not a problem because if you use formulas for each cell, then they're always cell consistent. Okay, so I'm looking for consistency between columns CD and the rest of the spreadsheet. That's basically what I'm looking for. So if you use formulae, right, it's not going to be an issue. All right, so let's go ahead and work on this one. The first two columns to work on, I kind of indicated that in class as well, are column G and column H, because you need to find out what the binary representations are. So in this case, there are easy ways to do it. In the spreadsheet, you can use, I think, base, and then you tell it what number you're converting. So in this case, it's this particular number. Radix is the base of the number of the conversion. So we're converting to binary, which is 2. And then the minimum length is how many bits should we use for that representation. So this will do it. And then we just do this, and then we do that. And now we are done with these two columns.
Wow.
It's a base, base conversion thing. It's built into the spreadsheet's capability. Yep.
Wow.
Einstein used to formula this to be.
Yeah, that to be is a more specific case. I think this is a more general one. You can convert to any base you want, including some really oddball bases like 5. Okay, so you want to bring base 5,
Have you ever worked in base 5?
You do base?
Have you ever worked in base 5?
Well, just think of one hand, right?
Oh, goodness.
Base 10, base 5.
Ouch.
Can't do that one.
Okay, so when this is all done, then we have to work with assigned numbers. So the first thing is I want you guys to kind of do it by hand a few times, just so that you get the hang of it. So in this case, the signed interpretation of 1101 is that 1, it is a negative number, and then how negative it is depends on the 2's complement of the number plus 1. Is that right? Okay? Okay. So one thing, there are many ways to answer this question. So I'll show you guys like a few ways to answer this question. So the first way to answer this question is, once again, use an equation. And I'm going to use 2's complement to do this. Okay, so we'll do a negation, a binary negation, and then plus 1 to it. Okay, and in the spreadsheet, there's no bitwise not. Okay, unfortunately, in LibreOffice or Excel, yep.
Well, I was going to ask, are those base 10 numbers or base 2 numbers based on your description above?
Which description?
Signed value in base 10.
It is interpreting the binary numbers as a signed number. So they should be in base 10.
Not base 2.
It says signed in base 2 on base 10 at the top.
Yeah, it says signed value in base 10. And once
Unless you interpret 10 as base 2, which means 2.
yes.
Okay.
Because we asked you about that the day we were doing in the lab too.
Yeah.
You said use base 10.
Yeah, use base 10. Yep. But I'm just making that joke that 10
I
is
see.
2 in
Yeah.
base 2. So some people say, but you say base 2 because 10 is 2 in base 2. Okay, if you don't get it, that's okay. Don't worry. Okay. All right, so let's do a bitwise not, okay? So how do you do a bitwise not when you don't have a bitwise not? We talked about that a little bit also in class. So with a 4-bit number, okay? With a 4-bit number, you basically say 15 minus whatever the value is, it becomes a bitwise not. We talked about that also a little bit in class. So I'm going to do just that. So I'm going to say 15 minus whatever the original value is, which is 13 in this case, okay? And then we say plus 1, okay? That becomes the absolute value of the signed number. But it doesn't work all the time, because sometimes this number is going to exceed 15, or it becomes 16 or more. So what you need to do is to do a mod so that it contains the number of bits of that thing. Okay, so we do a little mod here. Okay, so we say modulus, okay, and with modulus you specify the dividend, which is this thing here, and then you want to mod it with 16 so that the actual result will never exceed 16, because after all we're dealing with a 4-bit number, right? Okay, so you look at this and go like, oh, that's wrong. This is supposed to be a negative value. How come it is 3? Well, that's because 3 is the 2's complement of the value represented by 1101, which is negative. Is that okay? But 2's complement is the same thing as arithmetic negation. So when you take the arithmetic negation of the value -3, you get 3 back. So now the sign is wrong. Okay, 3 is right. Okay, but 3 is the magnitude of the negative number, which is correct, but the sign is wrong. So how am I going to fix that? All right, so you use an if statement. Okay, you say if, and you say, okay, if bit 3 of the number is a 1, then negate it. Otherwise, just copy the number itself, right? Okay, so how do we take bit 3 of the original number? In other words, I look at the binary representation of 13, and I ask the question, does it have bit 3 of 1 or 0? Yes?
Do you use the left command?
You can use the left command, okay? So we'll go ahead and use the left command first, and then I'll show you another way, okay? So we say the left of this particular cell is G4, left of G4, 1. If that is a 1, right, then we want to negate the 2's complement, because the 2's complement will give me the absolute value of the thing, but then I have to do an arithmetic negation to get back to the negative side.
I think I use double quotes.
Double quotes? Well, yeah, if it doesn't work, we'll fix that. That's an easy one. Okay, if it's not, okay, if it is not a 1, if it is a 0, we just copy whatever it is, from C4, right? So we just copy it from C4 in that case, and that should be the end of it. Press the Enter key, Yes, it works. Okay, but there's another way to do this. Okay, so let me show you the other way to do this. Okay, so there's another way to find out whether bit 3 is a 1 or not. Because we're dealing with 4-bit numbers, right? With any 4-bit number, if the unsigned interpretation is 8 or more, the most significant bit is a 1. So you can do an arithmetic comparison of the unsigned value to 8. So now you can say, okay, instead of using G5, instead of converting it into a binary representation first, you can look at C4, C5 in this case. So you can look at C5 and say if it is greater than 7 or greater than or equal to 8, pick 1, then it's the same thing. Okay, let's check whether that works for negative values or not. Okay, it works for negative values. Is that okay so far? Okay. So now we look at this thing here and go, well, is there any other way to do this computation? Well, as it turns out, there's another way. Now, when you look at the, okay, let me just extend this first, so that you can see the pattern. Okay. When you look at 13 and 3, 13 minus negative 3 is 16. 12 minus negative 4 is 16. 14 minus negative 2 is 16. Are you seeing that regularity? So that means if you are dealing with a negative value, you can actually do you can subtract the number in column C. You can subtract 16 from the number in column C to get to the answer. Is that making any sense?
Sounds like it.
Yep. Okay. So once you see the pattern, there are many ways to get to the answer. Okay. But for numbers that are actually non-negative, then it doesn't work. Right. So you don't want to universally apply this. So now we can go to this thing here and go like, well, this whole thing is a little bit easier to work with now because we can just take out all this mod and all the bitwise not, and instead we just say, okay, let's just take the number in C9 and then minus 16, which is 2 to the power 4, and that will give me the same values. No, that's right,
Okay.
because this one is not a negative. The next one is. So as you see, that works as well. Okay, so there are many ways to skin the cat. Okay. Yes. Okay.
Why did that come to your mind?
Yeah, exactly.
That's a colloquialism.
I don't know exactly how did that come about. So there are
There are
many
many
ways
ways
to
to
do
do
this
that.
homework assignment.
They see cats.
You can always do it manually as well. Okay, but the whole point is I want this to be so tedious, as there are so many of these, to make you think about a way to do it automatically. Then you think, okay, we can do it this way, we can do it this way, and all ways are fine. Okay, if you use a string way to do it, which is kind of long and cumbersome, that's fine too, because when you are working on your formula, you are thinking about the problem itself. So no time is wasted when you do this homework assignment. Are there any questions about the solution up to this point? Okay. Then you say, okay, but Tag, you only got one column done. Now we got 2 columns. That's the beauty of using a formula. Okay, because when you use a formula and it is correct, you just replicate the formula a few times and you're all done. Is that okay? But that really is the point of the whole homework assignment. I want you guys to find out the pattern of the whole thing. Is that okay? Yep.
Are you recording this? So this
I hope so. Well, I can even share the spreadsheet. I mean, that part is
Oh, okay.
that part is okay. All right. I'm going to share the spreadsheet because I think most of you, well, unless you kind of like pause the playback, you can still see the equations. But it is important for you guys to actually look at the equations and find out why it works. Okay, like why is there a modulus operator here? Why are we subtracting D4 from 15? And then later on, we are subtracting 16. From that number, why would this work? Okay, so all of these are questions that I want you guys to think about. Okay, because obviously they are all equivalent solutions. But why are they equivalent solutions? I want you to think about those things. Is that okay? All right. Okay. So when we look at binary sum, which is basically really just the least significant 4 bits of the summation of the two numbers, okay? There are many ways to do this, once again, okay? One way to do this is to basically use the base command again, which is converting the base because we want it in binary. So what are we converting into binary? That becomes the big question, okay? Addition is sign insensitive, okay? In other words, if you look at it as a bitwise operation, it's the same operation. Whether the bits are supposed to be representing signed numbers or unsigned numbers should not matter at all. So in this case, I'm just going to say, let's add this number to this number here, okay? And let's convert it into base 2 and use a minimum of 4 digits. And immediately we have a problem because now we have 5 bits, okay? Which is wrong, right? Because the binary sum should have exactly the same width as the original numbers. In other words, it should be 4 bits only.
That's kind of weird. You even told it 4 bits.
Huh?
It's minimum.
Oh.
Yeah, 4 is the minimum width. Okay. In other words, if the value requires less than 4 bits, then it will pad more significant zeros.
Okay.
Okay. So if I want to force this into a 4-bit number, I'm going to apply the same trick as I did last time, which is to use the modulus operator and mod it with 15. So how many people still remember what is mod? Modulus,
It's a
which
little
is
percent sign in.
the percent sign in C and C++, but what does it do?
It divides it and returns.
Yep, exactly. It returns just the remainder after a division. Okay.
Yeah.
So if you divide a number by, excuse me, not 15.
Yeah, you want to do
It's a bitwise AND with 15, but if it's a mod, it's 16. Okay. So if you divide a number by 16, what is the largest value of the remainder? 15, right? 15 is the largest remainder when you divide something by 16.
So this is like base 16.
It's forcing the number to
Exactly what it
fit
is.
within 4 bits. So I'm just going to write this on the whiteboard because it's something that you probably should learn from your C++ class. When you do a mod 16 in C++, it really is the same thing as saying bitwise operation using a single ampersand for bitwise AND with 15. Because 15 in decimal is 1111 in base 2. So these two are basically equivalent when it comes to integer arithmetics. Is that okay? All right. So I choose to use a mod operator here because I don't really have bitwise AND in a spreadsheet, but it will serve the same purpose.
Are we going to be using that by any chance?
Sorry?
In this class? With bitwise AND? Are we going to be using that in this class?
In this class, thinking about it, probably not.
Okay.
But it is a really useful operator. Do you guys know what is a bitwise AND? As opposed to a logical AND? Yes? Sort of? I see some people saying yes, please move on, and other people going like, no, I don't think it was covered in CISP 360. So I'll do a quick one, okay? So let's say X is a 4-bit number, okay? Well, make it a 6-bit number, okay? So X is a 6-bit number, so it will have X5, X4, X3, X2, X1, and X0 as individual bits, as a 6-bit number. Is that okay? So bitwise AND is really just a bitwise AND. I mean, it really is just saying, okay, look at the binary representation as individual bits for both of these operands, okay? So let's say we are doing the same thing here. We're doing a bitwise AND with 15. How do you represent 15 as a 6-bit number? Well, the same way as you represent it as a 4-bit number, but since we have 6 bits here, you just have to add zeros to these things, right? Okay. Then you perform a bitwise AND. What is X0 and 1? Do you get 1, do you get 0, or do you get X0 back? X0. Okay, so we get X0, X1, X2, X3. What about AND 0?
0, 0.
You get 0 and a 0. So the bitwise AND is forcing the most significant bits to become zeros by preserving the less significant digits. Okay. Is that okay?
Oh, so that'd be a way of like cutting it down to
Yes.
truncating?
It's for, yeah. It's kind of truncating in this case.
It's modulus.
And it serves the same purpose as mod 16 because it's doing the same thing.
So can you do that with any numbers, or does it have to be 15?
It should be unsigned. So, okay, so if you want to generalize this whole thing here, so x mod 2 to the power of n is the same thing as x ampersand 2 to the power of n minus 1. Is that okay? And someone's going to say, but this is syntax error. There's no superscript in C and C++. Fine. Fine. Same thing. You know, because the number of bits that you shift to the left-hand side is raising 2 to the same power. Is that okay? So once again, you know, this is important stuff that I feel is important when you learn C and C++, because the one thing that is really that C and C++ are really good for are low-level programming. Now, when we talk about low-level programming, it includes writing device drivers. Okay, when you write device drivers, you know what we call the I/O registers or input-output registers, they are bit-oriented. In other words, if this bit is a 1, that means the device is going to do this. If that bit is a 0, that means the device is going to do something else. Or if these 3 bits, and they may not even be consecutive, okay? If these 3 bits is 0, 1, 0, the device is going to do that. So you need to understand bitwise operations very well in order to write device drivers. And then people say, yeah, whatever. I don't want to write device drivers. It's some really obscure, you know, stuff that only a small percentage of people need to understand. Is that right? Think of all the mobile devices. How fast do these companies like Qualcomm or AMD, how fast do they come up with newer devices, the next generation of devices? Oh, every decade or so, maybe. Every 6 months? So some people have to write and maintain these drivers, okay? And as a result, understanding this stuff here allows you to take on those jobs because there is such a demand. Very few people understand this stuff well enough to feel comfortable to write device drivers. So as a result, if you are one of those few people, then you become a very valuable employee. Is that making any sense? More or less? Okay. Okay. So getting back to this one, you know, this is one way to do it. Okay. So now we look at this and go like, let's see whether that makes sense or not. Double check, right? So 1101 plus 1011 is 1000. Okay. Does it make sense? Well, we can check it in a few ways. You can actually carry out the bitwise addition and see whether 1000 is in fact the answer. But there's another way to do it. You can look at these two columns. -3 plus -5 is -8. How do we represent -8 as a binary number? 1, 0, 0. Okay. And how do we know that? Remember the number wheel? Yeah. So the number wheel will tell you that as well. Okay. So that part is done. Flags. Okay. This is the really kind of tricky part that I really want you guys to spend time on. Okay. The carry flag is a carry of addition. Okay. But the meaning of carry simply means, oh, okay, the sum of these two numbers can no longer be represented using only 4 bits. Okay. There's some excess to the value that has to be represented by the 4th bit or bit 4, which does not exist in the number itself. So once again, there are several ways to do this. Okay. If you want to go for the bitwise operation and just extract a particular bit as the flag, as the carry flag, you can do something like this. Okay, you can basically say we are extracting the binary representation. So we say base of the sum of these two numbers. So we say C4 plus D4. Okay. But we want to convert into base 2. Oops, I closed the base 2 early. We want to convert to base 2, but this time I want 5 bits instead of 4. Because the most significant bit in this case is the carry flag. Okay, so we just want to say, okay, give me 5 bits instead of, and then the left is just, taking the left-hand side x many bits, just take the one from the leftmost bit, and that becomes my carry. So that's one way to do it. And let's double check and see whether that works or not. Okay. Well, looks like it does work. No, it does not. It does.
There's no carry on the first one, is there?
There is one.
Oh, there is. Yeah. Okay.
Yeah, because 13 plus 11 is more than 16.
Yes, I see.
More than or equal to 16. Therefore, you have a carry. Oh, did I just spell out another solution? Yes, I did.
Oh my goodness.
Okay, so the other way to do this, instead of using the bitwise operations, is to go for the semantics of carry itself and basically say, okay, carry is a 1 if this number plus this number is greater than 15, which is the largest unsigned value you can represent using 4 bits, then we have a carry. Otherwise, we do not have a carry. Yep.
I have 16 because whenever I type more than, it still counts as more and more for people. And so instead I type 16 instead of 15.
You use a comparison?
No, they're exactly the same, but I type in 16.
But as a comparison, I use 15 as in a comparison.
Yeah. But when it's going to be 15, it's going to count as 1.
I was at 4% battery life.
That's true.
Let's find one that is the case, like this one. There's no carry in this particular case. 1100 plus 0011 is 1111 with no carry. That is the correct result.
Yeah, but you didn't extend this formula to that.
Fine.
Oh, that's weird.
Okay,
Minus-
so, well, okay, I have to take a look at your actual equation to find out why it is not working. But this one is working. Okay, so the next question is there another way to do this? Many cats will die today. Okay, is there another way to do this? Can we use, I don't know, mod to do this? Well, maybe not mod, but we can use floor, right? Yeah, go ahead.
I was gonna say, can you just look at the final?
You look at the 5th digit.
Yeah, the 5th digit.
The
Remember,
fifth.
remember how the binary sum had 5 digits?
Yeah.
You can just look at the
Which
fifth
is the
digit.
first? Which is the first one? This is using the 5th digit.
Oh.
Yeah. So that particular cat died already.
Oh.
We'll have a lot of dead cats and also dead horses.
You're beating the
Yes, the animal right people will have a problem with this class now. What are you guys doing with the cats and horses?
Killing the cats and beating the horses.
Yeah.
What else?
Okay. So what is another way to do this? How about division? Would that do? I mean, I don't like the conditional thing, okay? I don't like to have a conditional thing here. So can we do something about maybe C6, okay, we still need the addition. C6 plus, what was it again, D6? Okay, can we look at the sum of these two and say, what about this thing divided by 16? Would that give me something that is usable? Let's see.
If it's greater than 1, yeah.
Okay. Whoa, that is not the right answer. A flag cannot be fractional.
Just
Yep.
give it a conditional if, and you could always compare that formula to 1. If it's greater than 1, you know that it's bigger than the formula can represent.
That's one way to do it. Okay. But then for people who took cisp310 from me, when we talk about binary search, to be exact, we talked about a particular function, and most people forgot about it like right after the lecture. What was that function? Floor. So we can take the floor,
For 300.
and I think all the other parameters are optional. The floor function is returning the largest integer that is less than or equal to the number.
It's the birthday function.
Exactly the one.
Yep, so it will do exactly the same thing, okay, and we'll,
Based on just what I know.
Yeah, exactly.
Oh.
Lines in my knowledge.
there we go.
I don't think so.
Another cat just died.
I can guarantee you that.
But this is all, but I'm doing this, to basically illustrate not only the thing that I want to illustrate in this class, but also to illustrate the flexibility of a spreadsheet, and also what I want you guys to think about is why do these alternative methods work? Okay, because that ultimately is the most important part is why do they all work? Okay, now you guys work out one solution, that's great. Okay, you get full credit for the homework assignment. But I want you guys to understand, oh, there are other ways to do it too, many other ways in fact. Okay, so that's just a carry flag. What about the zero flag? That's an easy one. Yep.
I have a question a little off topic. You said flags cannot have a decimal, but is that the same case with quantum computing?
Well, in that case, it's not exactly a decimal. It is basically, a superposition of states, right?
Oh.
So now we have to bring out another cat, Schrodinger's cat. So another cat will
Both dead and alive
maybe
at the same
die,
time?
dead and alive at the same time, yes. Okay, the zero flag probably is the one that only has like one really sensible solution. You basically just have to add up the two numbers and ask, is that zero? Okay, if that is 0, then you want a 1, otherwise you give it a 0. And
You don't want to do that with the AD columns. You want to do that with the sine columns, don't you?
okay,
Because if you do it with the non-sine columns, you'll never get 0. You can't get 0.
what?
Because a positive number plus a positive number is always greater than 0.
Oh, well, yes. I forgot this one thing. Mod it with 16 first, because we only pay attention to the least significant 4 bits. I think none of these cases actually give me a 0, so they will all be still be 0. But I can always test it with a kind of artificial case. So I would just turn these two into zeros, and that becomes a 1. So that works. Just to verify that it does work. Okay, so I'm gonna resume back to what it used to be. Okay, the sign flag. What about the sign flag? The sign flag is one of the easiest. If not the easiest.
Left
Yep.
binary sum.
You look at the binary sum.
If it's a left digit.
Yep. So you can just say the left of
I-4.
the binary sum.
I-4.
Oh, I have to do an equal sign first. I'm missing an equal here. Equal sign, and if the left one character of this thing, just extract that, whatever that is. I don't even need the if, because whatever it is what I need. Is that okay? So far, so good. Now the overflow flag is the question. Okay, yes. How do we do this? 2 ways to approach this. Once again, you can use the bitwise thing to do this. Okay, so you can enter the bitwise thing. Okay, I'll do that first. Okay, it is not easy. It is a little bit cumbersome.
That is a problem.
Question?
I was just saying it was a pain because the syntax of like the formula in there.
Yes.
Was the like I can do it in C++ like easy.
Yeah,
I got it. But I was like, I can't
Do it on
tell.
Modulus super easy.
Couldn't tell this what. You know what I mean? Couldn't
Okay.
translate the C into.
Okay, so then there's a comment about when you use the actual bitwise operations, the representation is very cumbersome and it's difficult to track the parentheses and stuff like that. That's your point, right?
Yeah.
Okay. So I want to kind of tell you guys, or have an approach to do this, because trust me, this is not the only time that you have to deal with nested parentheses that are like really difficult to deal with. So there are techniques to kind of help this, make this a little bit easier. Okay. So when you look at the equations, especially for addition, you know that it is a conjunction. Okay. So you know it's a disjunction at the top. So you know it's a disjunction at the top with 2 conjunctions at the bottom, right? And with addition, it is not, and then not here. These 2 bits, this one goes up to here, this one hooks up to here. And they are the two incoming most significant bits. This is the bit of the sum itself. Is that okay? I hope you guys still remember this picture or the equation, right? Okay, so what we need to do here is to create the structure first, and then we go back in and fill in the actual details. Okay, so I'll show you exactly what I did with this, okay? So the outermost part is an if, and if the condition is true, we have a 1. If the condition is false, we have a 0. You can also just use true, false, and then force the columns to represent true as a 1 and false as a 0. That works as well, but this will automatically convert a Boolean value into a numerical value. Okay, so that's the part. So then you say, okay, the overall operation is an OR. Okay, what are we ORing? We're ORing the results of two ANDs. And how many things do we have in each AND? We got 3 things. Ding, ding. And those are 2 commas, and then 2 commas over here. So by doing this, you are taking care of the outermost parentheses. So now you only have to worry about the individual bits. And each one is basically the left block 1, right? Okay, so now we just have to specify, okay, which 3 bits are we talking about? Now with the first one, I'm going to take care of this one first. So we have the negation of that first, right?
G1.
So you can compare to 0 if you want the negation. So you can say left,
G1.
let's see, G1, 1, but then you have to compare that to a 0. The next one is left G2, 1.
No.
With
It's not G, it's I.
The wrong row.
H1.
GH, yeah,
And
GH.
it's not 1, it's 4.
Yep.
Yeah,
This is H,
H4, and the first one is G4.
H, yeah, G4. There we go. Or you can just click on the screen too. And then the last one is going to be
I4,
the non-negative version.
left of
I4 just 1 compared to 1.
Did you just take
Why do we need a,
Yeah, why do you have a 1?
Huh?
Why do you have a 1 after G4?
Why do you have a
G4
1 in the
comma
left?
Because he's
1.
doing G4 in a left command. He's got to grab just 1 digit from the left.
Isn't that what left does though?
Yeah.
Yeah, that's
left
exactly
is
that's what left does, but left will grab however many digits. It
No,
knows.
left will grab just the left digit. Like
Yeah.
you could just leave out the 1
So you can
with the
omit it?
comma.
Oh, yeah, left by default has a 1 as the length. Okay.
Oh, I
Yeah.
see.
Yeah, that's what we
But
did.
you're right too. We can just extract the sign column as well, which is already a digit. Okay, so that's fine. Here you can do it out. It looks clean, so we'll do that. Okay, so we instead of doing this, we just say that this bit has already been computed as I cannot see it. GHIJKL. Okay, so that's L4. L4. We tried it. Okay, so that's one side of the whole thing, and then the other side is kind of the same, except we're comparing to 1, 1, 0 instead, right? So now we just copy and paste it. Yeah, copy and then paste, including and overwrite these 2 commas. So copy paste, but change all the ones into all the zeros into ones, and then all the ones into zeros, like that. So okay, got my fingers crossed. Okay.
All together 0.
Okay, we have 1. Okay, so let's check whether that works or not. Okay.
Yep.
Okay, -3 minus 5 is -8. Okay, that works. All of these are working. Let's see the one that is not working. That one does not work, right? Because -6 minus 5 is -11, which cannot be represented using a 4-bit number, and it has an overflow of 1.
So it is working.
Yeah.
So it is working.
It is working. Yeah.
He's just saying that because it doesn't.
Now, are we ready for another cat?
So,
Which is a yeah.
so the definition
This is
is
probably gonna be
that
how easy that's gonna do.
the sign doesn't match with,
The sign doesn't make sense.
yeah, the sign doesn't make sense, that's the definition.
Yep, it is. Well, that's the semantic of it, okay?
We could
but
have
if
done
you
it-
use the semantic
we could
of
have
the
used
sign
the
doesn't make sense, that's another
original
way to do
columns
it. Okay,
as-
guys. Okay, because when you talk, people behind you cannot hear me either. I understand you do not mean to disrupt it, but it ends up doing that. So, excuse me. All right. So the other way to do this is to look at the semantic of the whole thing. You basically say, okay, the range of signed numbers that can be represented using 4 bits is -8 to 4 to 7, right? So you ask, okay, is the actual sum of the signed interpretation of the bits exceeding that range? If it does, it's a 1. So that's the other way to do this, okay? Using the semantics. Okay? So we'll go ahead and try the other method.
So basically if it's more than 7 or less than
Correct. If the sum is.
-8.
Yep. So you say if, and then you use the sum, but you have to be careful which sum you're using because we're not adding these two, we're adding these two instead. So you say if, okay, and then we have a range check. I don't think there's a built-in range check in Excel or in.
Do you need it, or can you just, you know how you use greater than or less than signs on either side of?
I don't think it will take it on either side. I think you can only take it on one side or the
What
other.
if you use a one and statement or
Let's
or
see.
statement. Use the or statement is less.
You have to use an or statement because you need one to check on one side and the other need the other one to check the other side, which is okay. We can do that. So we'll start with the or, and if at least one side is exceeding the range, it is a 1. Otherwise, it's a 0. So now we go back to here and say, okay, there are 2 components to this thing here, and each one is based on the comparison, and that would be column E,
E4
E5,
plus F,
5.
E4 plus F. Oh, no, you're right. E5
Yeah.
plus F5.
So if it is greater than 7,
Or if E5 plus F5
or
is less than
the same thing
-8.
is less than -8, then we have an overflow situation.
Damn.
And
Up 1 box.
copy the whole thing, and the ones should be preserved. Yep,
They are?
and they got preserved.
wow.
So that's the other way to do it, okay?
I know.
But these 2 ways are equivalent. One is using the bitwise operations, looking at the numbers, but not looking at the values. We're looking at the representation of the values as binary numbers. So that's the first approach. The second approach is using the semantics of the flag and say, okay, what does it mean when the overflow flag is a 1? What does it mean when it's a 0? So using the semantics or the meaning, now we have a different way of solving exactly the same problem. So once again, the 2 ways are equivalent. I want you guys to understand why they're equivalent, because sometimes when you're designing the processor, you have to use the first way. You cannot just tell the Verilog program and say, okay, look at the values. If it is exceeding this range, make it a 1. That doesn't work because it doesn't translate into logic gates. So when you're designing the processor, you have to look at it from the perspective of 1s and 0s, true, false, and logic gates and or not, that sort of thing. But as a programmer, what does it mean when the overflow flag is a 1? So to you, the meaning is, okay, we can no longer represent the result as a signed number, given the number of bits that we can use. So both interpretations are important, but you have to kind of connect the 2, because that's the most important part, is connecting those 2 concepts. Yep. Mm-hmm.
So the difference in these 2, as far as we're concerned, I would think are the first one translates to how the processor's already set up, whereas the second one we'd have to make like a completely different circuit because I think we could do it in Logisim, but it wouldn't make a lot of sense to make a completely different circuit just to find the overflow.
But there's a
I got all 4 flags showing up.
Yep. And the processor, later on today, in about 10 minutes, I will give you guys my quote-unquote, first revision, that kind of like a draft processor. But in the draft processor file, there's also the draft ALU, which also includes all of these calculations. So you can actually see everything expressed as logic gates. Okay, so but we'll talk about that when we get to that point. So now we have to deal with the binary addition or subtraction here. So we look at binary sum here. Okay, so this is the other trick. If you want to copy and paste but don't want to have to readjust the columns, make the columns absolute. When you add a $sign in front of the columns, It doesn't really do anything here because we're not copying and pasting yet. But this allows you to copy here, over here, and it preserves the column number. It won't do that unless you have a dollar sign. Without a dollar sign, the column is going to shift depending on where you are pasting. Okay, so without a dollar sign, it's called relative, and with a dollar sign, it is absolute. Okay, so obviously this is not what we want to do. We are going to do subtraction here. Okay, whoops, subtraction. There we go. Okay, now yeah, go ahead.
So we could, if you never gave us that copy of the columns, we could still do this assignment.
Yeah. You just have to kind of. It's just a little bit.
You have to do formulas, and it would change. The
Yeah.
results will change every single time you opened it.
And let's see if that works. Okay, is that correct? Okay, so we are looking at binary representation. I'll just pick a few. That looks right to me.
What about that -2, -2?
Which one?
Oh yeah, that's right. 'Cause we're subtracting.
Okay, it looks right to me. -6 minus -5 is -1. That seems right. -8 minus 2. Okay, this is the one that's going to overflow, right? Because you're subtracting a non-negative value from a negative value, ending up with a non-negative value. Okay, because you're exceeding, the limitations of a signed number. Okay, all right. So let's move on to the borrow flag. Okay, so what do we do about the borrow flag? You can always just do the binary division using the binary subtraction, but use 5 bits and then extract the most significant bit. That's one way to do it. Okay, but the other way is to look at the meaning of borrow. Okay, the meaning of borrow is basically just saying, okay, if C4 is less than C5 as unsigned values, okay, D4, sorry. If C4 is less than D4 as unsigned values, then we end up with a borrow, because borrow simply means you are trying to subtract more than what you have, right? So if it's a 1 here and there's a 0 over here, so we'll go ahead and check whether that is correct or not. Okay, but this has to do with the unsigned interpretation. So okay, this is a little bit harder to read. We are going to do that. There we go. Okay, that makes it a little bit easier, right? Okay. Well, that's why you want to take cisp310 from me, because people who took that class from me or have already seen all this. Okay, but this is really just an application thing, right? I mean, you guys have a screen that is much larger than the one that I'm dealing with here, because so you don't have as much of a problem. Well, the resolution. Okay, there's a resolution, not the size of the screen.
The size is like.
You can always use optical illusions. Go pick up one of those optical illusions and whatnot. Then you can quite easily and inexpensively have a 52-inch monitor. You just have to be like smelling the monitor. Okay, so let's see what makes sense about. 13 minus 11, there's no borrow. 1 minus 6, that's a borrow. 5 minus 13 is a borrow. 14 minus 11 does not have a borrow. Seems to be working. Okay. And then the Z flag, we can just borrow from the other one. No pun intended. And instead of, but H4 doesn't work anymore, so you kind of have to adjust it without the dollar sign. But it's no big deal, because you only have to adjust it for the first cell, and then you can still replicate to the rest. And once again, we are not doing addition, we are doing subtraction. Okay. Now with subtraction, there's no need to do a mod, okay, because subtraction will never exceed the range that we are dealing with. So there's no need to do a mod, but it doesn't hurt to do mod. It doesn't really give you the wrong answers. So let's check whether the only one that is a 1 is correct. 14 minus 14 is a 0. But that's the only one that has a result of a 0. So that seems to be working okay. Okay, sign flag. Okay, sign flag is something that we can also borrow. So in this case, I'm just going to put a dollar sign here first. so that when I copy and paste, the dollar sign is already here, it is already correct. See, with the dollar sign, it doesn't shift the referred column.
Which column are you looking at?
But for this one, you want to use, you want
Yeah, we wanna look at a
to.
different-
Oh, right, yes.
Yeah.
So this time I do want it to shift. Okay, so we want to look at N. There we go. You are correct. Okay, there we go. Okay, let's double check.
That works.
Is
One.
it like formatting left and taking the left number?
No, whenever it displays a string, it is automatically left justified. Whenever it displays
it's
a
treating it like
value,
a s-
it is right justified.
So it's treating it like a string,
It is a string, yes.
but then in all the other ones are being treated?
Actual numbers.
Oh.
The other ones are numbers. Well, if you want to, you can turn those into strings. In other words, instead of saying return a value of 1, you can always say, a string of 1. So that will make it, appear
That'll put it up
uniform.
left side.
Yeah, exactly. Okay, the overflow in this case is similar to the other overflow, except you have to tweak the zeros and ones, okay? And obviously copying and pasting this one is going to be a lot of hassle because there are a lot of references to the columns. So the other way to do this is to use the interpretation or the range checking one, because this one is a lot easier to work with. So instead of checking the result of an addition, we'll be checking the result of a subtraction. But that's the only way, that's the only change that we need to do here.
To add our dollar signs.
Yep, this time we need a dollar sign because we are referring to columns that we do not want to shift. So then copy and paste the one with the dollar sign over here. Okay, now this looks kind of funky because would that work? Because it's not shifting, but it's not only shifting, what it is not shifting is the column reference. The row reference on the other hand will still shift depending on where you paste. So we'll take a look at this one and see if it works.
Yeah.
It does work. Okay.
Nice job.
So we'll replicate it and see if it makes sense. Okay. So we'll check the ones where it is a 1. Okay. So we have.
Oh, we haven't changed it from plus to minus.
Sorry. Oh, right. All right. So do a subtraction instead of addition here. Always do QC, right? All right, so after QC, we have something like this. So we should not be looking at column C or D anymore because those are the unsigned interpretations. So we will be looking at column E and F. Those are the signed interpretation. So we look at the subtraction of these things. Okay, -4 minus 6 is -10, which cannot be represented by 4 bits. Ends up with a value of 1 as an overflow. That's good. -2 minus -5 is +3. It is okay. 4 minus -7 is +11, which cannot be represented by a 4-bit number. Ends up with an overflow of 1. So just by spot checking, seems to be okay. Is that okay so far? Okay. So the last 2 columns are really just comparisons. So in this case, it is really just if the unsigned columns, okay, like that. So if this is less than that, literally, give me a 1, otherwise give me a 0. And then with this one, the other one is the other 2 columns. Okay, it needs to refer to column E and F. So we look at this one and say, okay, let's look at column E and column F because we're dealing with signed interpretation. So we end up with that. Okay, so there's one column here that is not a part of your homework assignment. Okay, but it's a really good way to double check to see if everything is self-consistent or not. It's the L flag. Remember the L flag? So we want to check whether the L flag is working or not. Okay, it's the exclusive OR, right? Okay, so we'll check that out. So I'm adding this column, which is not a part of your homework assignment. Okay, so don't worry if you don't have it. So the L flag is the exclusive OR, but there's no exclusive OR. Well, let's see if there's any. Oh, it does have exclusive OR. Okay, so if the exclusive OR between the sign and the overflow is a 1, then, well, okay. L is the exclusive OR between those two, okay? But this time it may have a problem because one is a string and the other one is a number. So it's going to say,
Can you,
it does work.
Is
Let's
there a
see.
function to turn a string?
Yeah, you have to turn it back into a value.
I think you can do that with base again.
Huh?
If you use
Base?
base the number, comma 10, it'll change it into a base 10 number.
But that's the base 10 as a string, not as a numerical value.
Oh, that's true.
I think that may not work. So let's look into functions, and we want to look into, it's either a string or mathematical. So I'm going to look into string first, or text. So we want to convert a string back into a number. I think it's value.
Value with the
Yep, there we go.
text we convert into a number.
Yep, okay. So we just have to take the value of Q4 and replicate this. Okay.
And
So
you can do
that's
it
what it
again,
says.
No, you can change the. You can format the cells to just be.
You could.
Yeah, you can just right click and
Format
go
cell.
format cells.
Text.
So instead of Boolean value, you just say look at it as a number,
Or text.
then it'll all become zeros and ones.
Why is the XOR?
Which row?
Why is the zeros in some cases?
Why does it match?
If it's
Why does it
true-
match the sign like
Oh, I see what
exactly?
you're saying.
Yeah, so this is a 1, this is a 1, this is a 0. I'm just spot checking here. That's a 1, that's a 0. So it does seem to work.
It works.
Yep. So all the flags are kind of self-consistent, but the most important part is the L flag column should match exactly one of the two columns S and T.
Yeah,
Which one is it
T one.
matching?
T.
It's matching T because the L flag is indicating the ordering in a signed comparison. Then when you look at column S, which column does it resemble? Which column is it identical to? Between column S and column
Borrow flag.
the borrow flag, exactly. So
Borrow flag.
column O and column S are identical because the borrow flag indicates the ordering in unsigned comparison. Is that okay? So this spreadsheet is important in many ways because it really is not just, oh, okay, how do we figure out the flags by hand, and then how do we automate the process, but it's also relating the different flags to actual comparison that you need to do when you write a program. If you're comparing unsigned numbers, what should I be paying attention to? If I'm comparing signed numbers, what should I be paying attention to? Is that okay so far? Sort of? Okay. So I will save the file and upload it into Moodle because I think some of you may find it useful to, not to memorize everything, but to kind of understand why it works. Yep.
You take out the divider before you upload it.
Take out the divider. Oh, okay, great. I mean this thing here.
Yeah, that thing.
Okay, very good. So let's double check, make sure everything is good. Yep.
Save it again.
Yeah, it's already saved. It doesn't have a little flag on it. Yep.
So the signed comparison in column and the L flag column should be exactly the same, right?
Nope, they should not.
Should not?
They're only the same when you're comparing numbers that are not negative. Between this column and this column, you can see sometimes they agree, other times they do not.
What are you saying? The sign and the.
He was talking about the sign
column
and
T
the
and column
L.
U.
Yes. Oh, yes. Column T and column U should be the same.
All the time.
And in this case, they are. Yes, all the time. Because column T is representing what you want to do in C and C++. Column U is representing how it is done in gates. And they should be the same because that's because you want to implement, as a programmer, I want to check which one is larger, which one is smaller. As a programmer, you interpret it as column T. But that cannot be done in the processor unless you translate everything into gate logic, which is what column U is representing. And column U is relying on these two, and these two also have a bitwise operation equivalent equivalence to to get everything done. Yep.
I'm trying to figure out why we're preserving the columns in like E4 and F4 and the formula.
Oh, you mean
Dollar signs.
the dollar sign is the trick, because when you have a dollar sign in front of a column number, when you copy and paste it, the column number will not shift when you paste it. Without a dollar sign, it will shift, which means if you're copying from one spot and when you're pasting is like 4 columns to the right hand side, then the referred column will also change by 4. When you do not have a dollar sign. When you have a dollar sign, you're telling the spreadsheet and say, do not shift the column when you're pasting. So depending on how you organize your table and depending on what you're copying and pasting, sometimes you put a dollar sign in front of the column because you don't want that to shift. Other times you put a dollar in front of the row number because you don't want it to shift. And very occasionally you will have you can have a dollar before both the column and the row number because you're referring to one specific cell somewhere in the spreadsheet. Yep.
So you can have $E$4 and
yes.
That would, no matter how many times you copy it or where in your spreadsheet you copy it to, it will always be $E$4.
Yes, it would not change what it's referring to. And it can come in handy depending on what you're actually doing. Okay? All right. Are there any questions about this homework assignment? Yep.
This may not be so much about the assignment, but well, kind of. But I ended up just like for my binary diff, I've got just 1 0. I don't have the zeros padded because I couldn't figure out how to represent it in binary.
Well, I will have to see your submission before I can determine how to assign the points. Okay, any other questions? So I'm going to upload this right away before I forget. And in fact, I'm going to upload it to the homework assignment itself. So I'm going to upload it to here as additional files. So I'm going to add one more file. And it's called flags. Okay.
You've already got a flag, so it's like
I know, but we can use save as, right? It's flags answered.ods. There we go. Very seldom do I use that feature, to rename the file that I'm uploading, but this is one of those few occasions where it applies. All right, so you have flags and flagged answered as a part of the homework assignment. So this way, it's all contained at one spot, and you guys can just download it, take a look at it, study it. Is that okay? All right. Okay, so let's go back to the website and go back to signed numbers. We're still in the signed numbers, but this time I'm going to download, and this is a zip file. 2016 processor V1 version 1 is a zip file. So once we download, we can unzip the file. So I'll go ahead and do it on the command line, so I can show you what it looks like, what kind of content is in it. So it's in my downloads folder, unzip proc.zip. I should probably make a folder first. So okay, so it has 3 files in it. ALU.circuit, registerbank.circuit, and processor.circuit. Okay, so all of these are kind of useful. Okay, so we'll go ahead and take a look at least the ALU first, because I want to show you how the flags are done in logic gates. Okay. So java-jar, and then where I have the logic sim file, logic sim dash, and then we just say ALU. There we go. Okay, so this is the ALU. It is slightly enhanced because we have all the flags now. When you look at this portion here, that's how we compute the overflow flags. Yep. Yeah, go ahead.
You changed C out is still C out, but what used to be C out here is now
Right,
C.
because there's another C out somewhere else, so I use C and B as the actual output from the adder and the subtractor. Cool. Yep. So you can actually work this one. I mean, this one is functional. The ALU is functional all by itself. You can test it by giving it numbers. Okay, there are two numbers here. One number, another number. Specify what operation you want to perform. Click the enable bit so that the ALU is active, actually computing stuff. Then you can actually look at the output. You can also look at the individual flags as the output.
If you scroll down real quick, what's going on with that OR gate there?
This OR, exclusive OR?
Oh, that's an exclusive OR.
What do you think the exclusive OR is for?
L flag.
That's for the L flag, exactly. So I use a fifth flag for the L flag. So great, now that we have beaten the flag horse so many times, what are we going to do with that pattern? Run me. So what are we going to do with this, right? Start with the McDonald's.
Look at it. I don't even know this.
Well, this is what we're going to do with this. Okay, we are going to use these flags in the processor. Okay, so let's go to the processor design itself. It's inside downloads, inside proc, and here's the processor. Okay, require ALU.circ.
Because you have it open.
You haven't done that.
No, it's not because it's already open. It's because it's not
You
in
can
the.
select it. No, it's right there. You just
Oh, locate. I got it. Thank you. And then register bank is over here. There we go. So this is the processor at this point. I know it looks really busy, okay? But we only want to focus on one thing, okay? This is what we are focusing on. Okay, we're trying to track down the ALU and find out what we are doing with the flags. So this part is verifying just the ALU. This is the ALU, okay? The two numbers that we are adding. The enable pin to basically say yes, go ahead and perform the operation. The selection 3 bits will specify what are we doing. Okay? Are we adding, subtracting, bit shifting, bitwise and, bitwise not, or bitwise or. Okay, so those are the operations that we perform. This is the result, okay? But at this point, we are not so concerned about the result itself because we want to look at what are we doing with the flags. This is the flag out, which is the output from the ALU. It goes into a flags register, okay? Which is just a 5-bit register to store the result of the flags, okay? But the output of the flag register is going into this splitter here. So let's go ahead and take a look at the splitter and see what it's doing. So the splitter is feeding individual bits, okay? And I still remember, I think, the ordering. Carry, 0, sign, overflow, and the L flag, okay? So it's feeding those 5 individual flags into a multiplexer. And I'm also feeding 2 zeros into the multiplexer because I don't leave any input unused, okay, unattached. So I'm just replicating the 0. And the last one is still just a 1. You go like, oh, why do we want to do that? Why do we want to use constants, feed constants into a multiplexer? Well, that has to do with where it is going. It's going to, remember this is called a tunnel? So it's going to a tunnel called PCMux. So we want to find out where PCMux is hooked up to in this whole scheme. PCMux, Program Counter Multiplexer, right? Okay, so when you look at this whole design and go like, whoa, you know, I cannot see. Well, you click it. So what you do is you click.
You gotta do one more zoom in. Or
I guess zoom in one more level. So if this is highlighted, the other end is going to be highlighted as well, which is down here. So now we look at this part here.
The two places.
Never want to see that.
Okay. This doesn't give me, for those of you who like to contribute to open source projects, I would like a tool that allows you to drag a circle and it will just zoom into that portion. Okay, that would be very handy.
We're gonna have to be able to.
We should start with that.
I think that would be a great project for the student club.
Page to
You know, just have an open source project. You know, to add one little feature to Logisim. Okay, taking you through the whole process. What is revision control? How do you add? You know, how do you modify? How do you understand somebody else's code? What are the steps? How do you make modifications, test, and then upload everything to the repository? That's really a great exercise. Okay, but getting back to here. So this is PC mux, right? PC mux is the selection going into this mux here. This mux feeds the program counter. In other words, it's determining what is the new value of the program counter. And I'm missing one enable.
Yes, you are.
Okay.
That's an easy cloud line.
It's an easy one. I think it only has to be a constant too.
Can you draw that line straight over?
I think it only has to be a
Down,
constant.
down.
I'll deal with that later. Okay, but this mux is selecting how are we updating the program counter. In one case, we are using this to update the program counter, which means we're just going forward. And then in the other case, I think I got these two flipped. In other words, they should be exchanged, but it's okay. The concept is still the same. The other one is going into the demultiplexer out of the register bank. In other words, now we have two ways to update the program counter. The program counter can be just auto-incrementing, go to the next location, the next location, the next location, or it can take the output out of the register bank, which means one of the 4 registers can now provide the value. And if you follow the demultiplexer all the way around to the mux here, so that means I can use a register from the register bank to update the program counter itself. So if I preload a register with a particular location in memory, now I can say branch. Okay? I can alter the execution path. Instead of just doing a sequence, now I can say, oh, I don't want to go to the next instruction anymore. I want to go to that instruction over there. Okay? But how do we decide
Can you
where
have
to
multiple
go?
RAM modules though to be able to like house the next instructions? Like,
Well, the RAM module
or
is
it's not
really
necessarily-
just the RAM module.
you
The
could
RAM
discern,
module,
like, where section in your RAM module you're looking at. You could
This
jump
is my
to the
RAM.
section there.
but the RAM is contiguous. There's no quote-unquote section, right? I mean, this is really just a contiguous chunk of memory.
Yeah,
All I need to
like-
do is to say continue execution at 6.7.
Yeah, you just change where you're looking.
Right. And this picture is actually fairly complete, other than that one pin that I missed, which I think can be a constant. Well, maybe not, because it's a program counter, so I don't want the program counter to keep updating every single clock, because otherwise it will keep incrementing every single clock, which is not what I wanted to do. Okay. So I would need a special thing to attach to here. And then okay, so let's zoom out again. So are there any questions about this part? How we are using the flags? Yep.
Well, okay, so the flags are going to go into the PC mux. So
Right. So if I just focus on that portion of the picture, we have a multiplexer taking the flags and the 0 and the 1, right? So there's a 0 and a 1 here, and then we have the flags C, Z, O, S, L, and so on, right? So this is a mux, and there's a particular thing controlling this part here. Is that okay? Okay, so this is actually, I think it's called PC mux. Because it's a multiplexer that's to select what goes into the PC mux, right? So it's called the PC mux. Okay, so this is PC mux squared. Okay, so I pick one of these, okay, to go to this PC mux here.
To go to that
Okay? So as the selection of that mux.
Oh, yeah.
As the select. Okay, so I use this to help me select, okay, this is a 0 or 1 because there's only one bit. As a result, I can either select the auto increment, which is just saying, okay, let's move on to the next instruction. Let's move on to the next instruction. Let's move on to the next instruction. Or I can select the other one, which basically is a register from the register bank. So if I can preload one of the registers with a destination location and say, that's where I want to go to continue execution of this program, now I have a path to feed this into the program counter and update the program counter accordingly. So I can do conditional branch, because I can first perform a comparison or subtraction, right? And then I look at one of the flags, just pick one. You can pick Z, you can pick L, you can pick S, whatever. And that in return is going to be used to do this.
So anytime you get that particular value and PCMux squared is telling it to read from that value, it will always jump to some other
Well, predefined place.
well, it will be predefined, yes, but
But yeah.
It's
You're
predefined by
basically
another
waiting,
register.
you're
So
waiting
what-
for the
what-
flag as your cue to do whatever you're gonna move wherever you're gonna go.
yeah.
I'm just wondering what the relationships are gonna end up being, and I guess it kind of depends on the mux squared.
The mux, exactly. So the mux square is now the biggest question, is who is controlling the mux square? Okay, so we'll track this down and then we'll conclude today's lecture because we are running out of time. But I can tell you the next homework assignment you get is to work with this design after I fix that one unconnected pin, right? So you'll work with this design and then you're going to work with, guess what again? The music box. So the mux is hooked up here.
What's Ucode?
Ucode is microcode. U is micro. So mux, oh, where's mux?
That's up higher. It's up
I know,
higher.
but where is it hooked up to? I think I missed that connection to.
Yeah, where's it coming from?
Oh, we have it missing. Darn. Okay, so another thing to fix. So I've got two things to fix and two things that are not connected. But once I fix it, then it will be ready to do like microcoding. Just one last thing. Okay. There is a file in this thing called proc.txt.
Make little things
Oh, I
switch
guess
places.
a processor.txt.
In a way. Like
Nope,
our
I guess
Modulus
not.
might
Oh
do.
man, I thought I included that into the zip file.
I'm sure you'll fix it.
Yes,
I know, right?
we'll talk about this next time. Yep, next time. Until next time.
Are we doing a